So this is the first project in DC where a private residence is taking in public water off the street, and we're trying to maintain it on site. The rain gardens take all of the site water, and the roof loads will get funneled into this rainwater cistern. It's about a 1,000-gallon cistern on either side of the houses, with an overflow into the rain garden.
The houses are relatively simple in terms of floor plan. They have south-facing living and kitchen area, and on the ground floor there's a bedroom towards the street and a large entry area, a full bathroom downstairs with a laundry. And then when you go upstairs, it's an open stairwell that gets you to 2 more bedrooms and again a full bath.
An interesting thing about the design, the students worked with the community to kind of get a feel for what is typical in DC. And while the project is pretty modern, I think, for the neighborhood, and that's sort of what they were asking for, they wanted to maintain a lot of the outdoor living space, which is very important in DC. So the front porch, while very different than a typical front porch, is very common in DC, and that interaction between the street and the house was pretty important.
This is a view of what the house looked like from the mall, so you get a sense of what that large open living space was. And again, working with the community, we heard what kinds of things they needed in the house. So it has a very large kitchen and multi-purpose dining area, but we also were able to fit into it desk area so that parents could oversee their kids while they're studying for work. And so then construction was multi-phased. First phase was us. We actually had a beautiful site on the Hudson River, overlooking Freedom Tower, where we were competing to see who would finish first. And so you can see the module under construction there, which was both panelized and then later modularized. So on the left-hand side there is our unit going in. We were the only ones not to use cranes on the mall.
And this is the house coming to the site in the Deanwood neighborhood. For a foundation, we built a series of chain walls for a couple different reasons. We're in a 40-year floodplain, so the house had to be elevated to a certain height, but it also made it a lot easier to bring in the 2 modules and set them into place. So after the modules were set around in the middle of January of last year, or this year, we started to stick frame the rest of the second floor of the first house and then the second house altogether, working with our volunteers. Here's some of the details. So our exterior wall, we used a engineered I-joist on end, filled with dense packed cellulose and sheathed on both sides. Wall assembly. Doesn't show both sides, but we're looking at from the inside out. We have our gypsum wall board, then a dummy wall ranging from a 2x3 stud to a 2x6, depending on the mechanical system. Then our first air barrier, OSB, our main wall cavity, the TJI with the dense packed natural fiber cellulose. On the outside, you can't tell, but it's a zip system, taped with this fully taped and sealed. Then we have a rain screen and then cedar siding. This project started as a modular house. When it came to DC Habitat, we started stick framing it. We found it was pretty easy to stick frame it for us, working with our volunteers. We used tape to seal our air barriers, which was much easier for us to do with volunteers compared to the caulk that we used to use. A lot easier to control where volunteers were putting tape as opposed to caulk. Some of the inherent problems with the air sealing of this project was that party wall, and also working with a house that had been moved a couple times. We had our movers come down, bring down both parts of the house in 2 different trips. And on the first trip, the movers hit an overpass which knocked that first module out of rack significantly. But then on the second module, they knew that they were going to see that overpass again, but they just went right for it. I'm sure they just closed their eyes and went for it. But so the front corner of the house got beat up a little bit, but we were able to seal and fix it.
About a month ago, we got our, you guys have been doing
passed our blower door test finally, yeah. We did, I think, about 3 or 4 blower door tests, starting with the initial exterior membrane and the TJIs before we insulated. And we weren't achieving a 0.6, but we were pretty close. Once we insulated and sheathed the interior, we were achieving the 0.6. So having that dual air membrane was pretty helpful for us to ensure a full 0.6 EC.
So the other aspect of this house is the daylighting and lighting strategy. And again, we had, so students were very careful to design the overhangs properly using PHPP, but also using programs like Ecotect. And they worked very carefully on the window detail. So again, we used a beautiful wood into this window, which had a really good U value of 0.09. But it was installed with an insulated layer on the outside. But then, in addition to that, the students worked on creating this chamfer detail, which works almost like an ornament because it was, it was installed at the end after the window has been put into the unit. And so here's all the various steps that the students laid out very carefully so that when you guys took it over.
Because this is not a typical habitat for the humanity window.
But this is what it ended up looking like, and that chamfer was, again, really important. It allowed more daylight to get into the house and could right-size the windows, but it also helped to reduce the glare, so that thick wall was, felt really comfortable. And again, here's shots of the daylit house. Our lighting design group at Parsons also had a really nice lighting strategy, which was to basically take a conventional commercial lighting strategy of a low-level ambient and high task light, that created kind of layers of light that animated the space at the nighttime. And so then all of that allowed us to have a small mechanical system. And do you want to talk about that?
Sure. Pretty simple mechanical system. We, for this project, are working with a Mitsubishi short ducted air handler on the first floor, running supply, heat, and AC to the bedrooms and the living spaces.
Zender ERV is to the left of that, and a heat pump hot water heater by Air Generate, the air trap model. And the interesting thing about that is the students had designed a very small washer dryer closet just off of the mechanical room. And they wanted to help optimize the heat pump hot water heater by ventilating the air when the dryer was on into the mechanical room. So there's a booster fan on the in the closet to help channel the air into the mechanical closet for the water heater. And we also located our inverter in that closet, so that differential helps to make that heat pump hot water work better. And in addition to the building systems, we incorporated a fairly simple controls and monitoring system using some wireless parts and monitoring things in blocks. So we have monitoring all the plug loads, we're monitoring equipment, and also monitoring environmental quality of both houses. So we're really excited to see once the homers start moving in, what how the house works and how user behavior affects the homes. So all of that meant that our PV array was very small, 4.2 kilowatts on the mall and 5.2 in the Deanwood site. And again, it's designed to carry the loads of the house in an all-electric house. And that led us to win the affordability contest because our PVs, again, because of the passive cost strategies, were about a third the size of any of the other of our competitors. We had a team trying to do a net present value analysis of the house so we could understand what the costs were. It's very complicated and it is really not a reliable analysis simply because of the sponsorship nature of this project and also all of the things that we put into it, including the learning curve. But they were hoping, and I think that's optimistic, that all of the pieces that increased the cost would be about 15% total, and then looking at an 8-year payback for those pieces. But mostly, the most important part, again, for the homeowner is that we did some monitoring of existing homes in the neighborhood that were of equivalent size, and looking at their energy bills, which were about $2,000 a year. And again, students were comparing what happens when you get a low energy house, what happens when you get a passive house. Interesting, you see the lower green pies change so that the heating and air conditioning and hot water load gets reduced and lighting appliances, et cetera, gets increased. And then we end up by adding the PV and getting to net zero so that our homeowner, like Kia, will actually not have energy bills.